Hello everyone, I'm Chirag. I'm here to present our paper, Accurate Detection of Illegal Dumping Site using High Resolution Aerial Photographs. The presentation is structured as follows. We will start with the introduction and motivation for the study. Next, we will go to methodology, where we'll discuss about the data set used, the deep learning model which we employed, and the proposed dumping site recording pipeline. Then we will look into the results of our proposed model. Finally, we will discuss about the limitation and for possible future works and conclude the presentation. Waste management has become one of the major challenges faced by most of the governing authorities. According to Eurostat, between 1995 and 2019, waste produced by EU 27 countries has been increased by 8%. Another study shows that by 2050, the daily per capita waste generation in a high income countries is predicted to be raised by 19%, while 40% in low and middle income countries, which is alarming. The increase in overall waste generation is directly correlated with the increase in illegal dumping. The illegal dumping in the open space has a significant effect on human health. Uh, there are various smart waste management techniques employed by the city authorities, such as community based, IoT based, and volunteer mobile app reporting based. Most of these waste management systems are for a structured waste, but less attention has been paid on the unstructured waste, like the illegal dumping. So there is a need for automatic detection of these waste as fast as possible for a reason of hygiene and environmental protection. So in this study, we will focus on developing a method for detection and reporting of illegal dumping sites using high resolution airborne images or the high resolution drone images using deep learning model. The availability of the high resolution imagery together with the computer vision and deep learning provides a new opportunity for better monitoring of illegal dumpings. But the problem with the high resolution images, they are mainly highly imbalanced towards one class, that is a non-dumping class. For example, in high resolution images, it mostly consisted of urban infrastructures, building, houses, agriculture parcel, waste bodies, spanning a very vast region. So the annotation of such data is labor intensive and also very tedious. So this motivates us to employ synthetic data approach, where we will enrich the existing data set of remotely sensed images using synthetic images. We employ iterative process to generate synthetic images covering diverse data distribution. So coming to the methodology, um, in this study, we employ 2018 IEEE DFC dataset. So it is an urban land use and land cover classification dataset, which consists of very high resolution images spanning between this coordinate for the city of Houston. There are 14 images with a resolution of 11,000 cross 12,000 pixels. And the pixel resolution of this images is a 5 centimeter GSD. The images covers both urban and semi-urban region of city of Houston. So in data preparation stage, while data preparation, we extracted image patches of 256 cross 256 using sliding window cropping cropping with a zero stride. The main reason for choosing 256 cross 256 image patch size was this patch size is equivalent to 10 meter by 10 meter grid size, uh, which is an ideal area for visual inspection of dumpings for the authorities. The image patches, which were then manually annotated into dumping and non-dumping classes. And during this phase, we obtained around 200 image patches, which consist of garbage or dumping or waste items on it. So out of remaining and these 200 images were used as used for ground truth. That is, the natural dumping images are used as the ground truth for the evaluation. Out of remaining 2000 images which were chosen, which were around 2000 images were chosen as background images for generation of synthetic images, and around 16,000 images were used as a non-dumping image class. The size of um, uh, the non-dumping image was taken larger compared to the synthetic images. This is just to not repeat the same images while doing an iterative process during synthetic data generation. Uh, in during in synthetic data generation, we use the background images which we extracted earlier, which were dot annotated. That is, a dot were placed in a location where was likely dumping could occur. We used Blender and open source 3D software to generate the synthetic data. Uh, the 3D objects were placed on images based on the location determined earlier, generating an incidence of dumping classes. This process was automated, and the percentage of objects and type of objects in each images was controlled to generate diverse distribution. This generated synthetic data was used to train an basic CNN model, and the trained model was used to test on natural dumping images. The precision and recall of this is noted, and we continued this in an iterative process till we achieve an desired precision. Here we had 5 iterations of 5 iterations to generate synthetic data, and by the end of the data generation, we had 16,000 images in a non-dumping class, and 2,000 images on dumping classes. These are the synthetically generated images. Uh, we developed two deep learning classification model. One is the basic CNN model, CNN classification model, and other one is the deeper residual log classification model. The basic CNN classification model, it was used to create a baseline and provide feedback for generation of the synthetic data. While deeper residual blocks, it was used to measure the it was actually used to measure the precision and the accuracy of our proposed solution. The residual block model consisted of two blocks, that is typical residual block and a downsampling residual block. We use a combination of these two to build a residual block classification model. While training, we added 20% of real dumping site images on the training set. We also employed different augmentation techniques like rotation, color channel shifting, blurring, brightness control, and also vertical and horizontal shift. The training data was split into training set with 80% and the validation set of 20%. Um, Both models were tested on natural dumping images, and their results were noted. So we see that both the models had a better precision compared to recall. Here, precision measures the percentage of image that were correctly classified as dumping. We also experimented while generating synthetic data. We also experimented generation of synthetic chart data in a step ways where we added different types of 3D object on each step and recorded the precision on recall. We see that every time we add diverse data and have a diverse distribution of data, we the precision and recall, the performance of the model increased. That is, the precision and recall increased. The dumping detection, we also developed a dumping detection system using a Python. So actually, it took image patches in a with the 256 cross 256 size using a sliding window cropping with zero stripe, and fed it to a classification model. The classification model predicted the class of the image patch, that is either class 0, that is non-dumping, that is dumping, or class 1, that is non-dumping. So the the image patches which were predicted as dumping, those coordinates were recorded, and these coordinates were converted into geo coordinates and visualized in a GIS software. Now coming to the limitation, although our solution was able to precisely detect, correctly predict the class for most of the images, that is dumping or non-dumping, there are few image patches which were wrongly classified. So the confusion mainly occurs due to the characteristics of those images which contain visual features that are very similar to the waste dumping. This can be solved by adding more training data and covering a wide, diverse data set. But yeah, so this limitation can be solved with having larger, more data, training data. The other one is the proposed solution. The proposed approach requires high resolution image to work properly. So it is questionable whether the real classification model would work on lower resolution for the aerial photographs or the satellite photo imagery. That is the images which are around 50 centimeter or less than 50 centimeter pixel resolution. Uh, the future in future works, the future effort will be focusing on improving our classification accuracy uh, by of the proposed DL model and evaluate more complex and larger data sets. So we'll also in this experiment we had a limited number of natural dumping sites. So testing it on a larger data set would give a more robust and accurate results. Um, we'll also try various optimization techniques while generating more complex synthetic data, which includes low represented incidence of dumping, which we discussed in the limitations of this proposed algorithm. So we'll try to have more data of the low represented samples and get a better result. Finally, we'll also try to develop a complete solution for the authorities, which includes web applications and mobile application, which will also guide the city authorities or the municipal authorities to show the direction for the to reach the dumping sites and also effectively manage it. Coming to the conclusion, in this paper, we presented a method for accurate detection of illegal dumping sites from high resolution airborne images based on deep learning. The result showed that the proposed solution solves the problem with the high precision and with the minimum manipulation. It constitutes a promising technique for a problem which deals with similar, highly imbalanced or very limited data sets. Here are a few references which I used. Many thanks for your attention, and I'm here for your question.